So anyway, so this talk is actually tied into the previous, to the DART project, and I'll tell you why. So so this work was about the understanding that at the core of many cyber-physical systems are what we call software with timers and clocks. So software that actually has to measure what the current system time is, and then based on that do computations and set alarms in the future to make sure something bad doesn't happen. So a very good example is a scheduler or a budget enforcer that's trying to prevent certain threads from reaching their budget. So if we talked about denial of service kinds of attacks. So imagine we had actually some kind of mechanism by which we had some fairness condition. So we ensured somehow that no thread hogs up more than a certain amount of CPU cycles, and then every thread gets at least a chance to execute. So that could be a mechanism to guard against some kind of these attacks. So anyway, so it's in our case, what we wanted to do was to formally verify that what we call these timing enforcers are correct at the source code level. So it turns out that these enforcers have been widely studied, and people usually prove them correct at the algorithmic level, but then they go and implement code in C, and they use various kinds of low-level features to measure the clock, and then do all kinds of 32-bit arithmetic to do computation. So how do we know that the code actually reflects the algorithm? And the particular target we used for this was the ZSRM scheduler. So if you recall, that was the scheduler we used in the DART project. So in this project, we are trying to prove that the scheduler that's in the runtime system is actually correct with respect to timing budget enforcement. And to the best of our knowledge, this is the first time anybody has proven source code for these kinds of schedulers in a formal way with timing properties. Okay. So we want to verify source code because we want to push it down, assurance down to the executable level. So you may have heard of projects like CompCert. That's a verified compiler that takes C code and produces functional equivalent binaries. So our goal is to produce correct C code, and then maybe we can combine it with CompCert to get correct binary. So we're working in a broader ecosystem of a lot of other projects that are trying to produce verified binaries. And the other thing is, we don't need to sacrifice performance. Having the ability to verify C means that we can do all the kinds of tricks that low-level system code do. And then we can integrate with existing infrastructure. So in particular, the ZSRM scheduler that we verified is available publicly as a Linux kernel module that lets anybody who is interested to try it out and has a Linux installation download it. I'll give you the link at the end of the paper, and compile it and run it and play around. It has all the verification information in it. They can reproduce the verification on their own and make sure that everything is working as expected. So essentially, we want to get to what you verify is what you execute. So autoactive verification is actually a kind of formal verification where it's inspired by the Hoare, Floyd, Dijkstra style of deductive proof. So you start with a program that has functions and loops, and you add contracts. So you add pre-post conditions to functions, and then you add loop invariants. And then in the old days, you had to do a paper pencil proof that your loop invariants were inductive and your pre-post conditions were correct, and that was very tedious. What has happened recently is you have this big explosion in SMT solvers and automated theorem provers, and a lot of these, constructing these verification conditions and checking them can be fully automated, and that's what tools like FramaC can do actually. So you take C code, you write down the pre-post conditions, the loop invariants in a language called ACSL, and FramaC does the rest for you. And that was our approach to proving the correctness of this scheduler. So essentially, if you look at what happens in the scheduler, you have a set of threads, and threads are preemptive. So because they have priorities, a thread with a higher priority could come in at any time and basically push you out of the CPU. So the execution of a thread can be broken, of a particular thread can be broken down into a bunch of chunks, where what happens is other threads come in between and stop you from executing. So threads themselves are not atomic. They can be preempted, but we know that there are other critical OS functionality that is atomic. So when a signal handler, a timer handler goes off, it actually, one of the first things it does is disables all interrupts, so it can execute on its own without getting preempted. And the other thing is when new threads arrive and existing threads depart, they call special system calls, and these again execute atomically. So this is crucial for our verification because we are really interested in proving properties as invariants over what we call these enforcer functions. And we know that these enforcer functions execute without preemption. And so if you look at an execution of the system, you can think of it as built up of a sequence of transitions. Each transition is either a chunk of a thread executing or some action that denotes a thread arriving or departing. So this says thread 1 arrived, then a bit of thread 1 executed, then thread 2 arrived, and then thread 2 got to the CPU because it had a higher priority, and then thread 2 was done, and then before thread 1 could resume, another thread, tau 3, arrived, but it had lower priority, so even though it arrived and it's active, thread 1 was given the CPU, and then some timer handler went off, etc., etc. So any execution in the system can be actually thought of as a sequence of these transitions, some of which are atomic, which are the enforcer functions, and the others which are essentially just chunks of execution of the application level threads. So if you use that intuition, we can actually start defining what we call the CPU usage by a thread. So the CPU, so given an execution, the CPU usage of thread tau 1 is essentially you take all the chunks of all the transitions where tau 1 got to execute, and you take the amount, the duration of that. So the duration of this one is C3 minus C2. This is where tau 1 got, and tau 1 got another slice here, so that's C8 minus C7. So the execution of tau 1, the total time it got to run is the sum of these two durations, and so on and so forth. So you can define, given an execution and given a thread, the amount of CPU cycles that the thread got. Now, what's important here is this is a ground truth definition. We can never really measure it precisely because we can never measure time precisely, right? When you go and you say get time of day, the value you get back is not the value of time. It was the value of time a little before when the actual hardware timer got pulled. So there is always an imprecision in our notion of time, how precisely we can know time. But what we did as part of this work is to figure out a way to over-approximate this because we really need to be conservative. We just need to make sure that the thread did not exceed its budget. If it got a little bit less, that's fine. So that's the key idea is sort of using some formal proofs and some engineering, we can figure out a way to over-approximate the CPU usage, and now we can use that to budget and make sure that the threads did not exceed their budget. I'm not going to explain this theorem in more detail, but this is the key result. It basically the most important part in this part, which basically shows that the actual CPU usage of a thread can be over-approximated by some ghost variable. So you can do accounting using extra variables that over-approximate the CPU usage. And then if you set your timer using this value, which is an over-approximation of CPU usage, then you can prevent the actual CPU usage to never exceed the budget. And that's the key idea. That's kind of highlighted here. You have to set your timers in a way that the time at which the timer goes off is no bigger than the time that the thread has left, right? So that's setting the timer conservatively. And if you can do this consistently, which we can show in the code that we are doing, then you're safe. No thread can exceed its budget. And there are some results that basically show how to do this for both periodic and aperiodic threads. Okay. We have all the code that we use to verify available publicly. It will compile on a recent Linux distribution. I think Ubuntu 16.04. Ubuntu 16.04? 16.04. And we used Framacy, the latest version available called Aluminium, to verify this. And I think that's how they spell aluminium because they're French. And there's a paper under submission.